In Lesson 3.4, we will discuss exponential and logarithmic equations. In Video 3.4.3, our learning target will be for students to be able to solve logarithmic equations. The one-to-one property of logarithmic functions states that for b greater than 0, when your base is greater than 0, and your base is not equal to 1, then log base b of x is equal to log base b of y, if and only if x is equal to y. Some examples of that are log base 2 of x is equal to log base 2 of 6. If that is true, then x is equal to 6. If e is equal to y is equal to 2, if e raised to the y is equal to 2, then the natural log of e to the y is equal to natural log of 2. Now, what they're doing in this second example here is they're taking the natural log of both sides, and the natural log here, natural log of e is equal to 1. So the power of y can be brought out in front using the power property of logarithms, and you would get y times the natural log of e is equal to natural log of 2. And ln of e is equal to 1, so y is equal to natural log of 2. Now, alternatively, if e to the y is equal to 2, you could also state that if e to the y is equal to 2, then natural log of 2 is equal to natural log of 2. Because what we're doing there is substituting in the second equation. If I use my handy dandy eraser here, if I go back and erase there, in the second equation I can substitute for e to the y. I can substitute 2 because in the first part of the conditional statement e to the y is equal to 2. So I can replace e to the y with 2, so you get natural log of 2 is equal to natural log of 2. In the first equation, then since I solve for y, then I would make a substitution in the first part where it says e to the y equals 2. Then I could say since y is the equivalent of natural log of 2, you're saying e raised to the ln of 2 is equal to 2. Well, that's because e and ln are inverses. Natural log and e are inverses, so they would cancel out and you would be left with 2 equals 2, which is a true statement. In example 3, part A, we're asked to solve not an exponential equation. I don't know why the book wrote that, but it's supposed to be a logarithmic equation, and I'll abbreviate that as log, using the one-to-one property. Now, what we have here is log base 2 of 5 is equal to log base 2 of 10 minus log base 2 of x minus 4. Now, to use the one-to-one property, we have to have the equation down to a single log on both sides of the equation, and the logarithms that we have on both sides have to be the same base. Well, that's not going to be a problem here because all of our logarithms have a base 2. So I'm going to leave the left side of the equation alone because I already have a single logarithm or one logarithm on the left side of the equation. On the right side of the equation, I'm going to combine these two logarithms using the quotient property. Since I'm subtracting the two logarithms, I can divide the inputs of those logarithms. So log base 2 of 10 minus log base 2 of x minus 4 is the same thing as log base 2 of 10 over x minus 4. Now, what I want here is I'm going to use the one-to-one property since I'm down to a single log on both sides, and log base 2 of 5 is equal to log base 2 of 10 over x minus 4. Basically, what we're saying is that my inputs have to be equal. So some people cancel out those logarithms because basically we're stating that if the two sides are equal and both the logarithms have the same base, then our inputs are equal. and ultimately we're trying to solve for x. So if I'm going to solve this equation for x, I have 5 equals 10 over x minus 4. I'm going to put a 1 underneath my 5, and then I have a proportion. Two fractions equal to each other means that their cross products are equal. So my first cross product is 10, and that needs to equal my second cross product, which is 5 times x minus 4. And if I multiply that out, I get 10 equals, I'm going to distribute the 5. I get 5x minus 20. And solving for x, I would add 20 to both sides, which gives me 30 equals 5x, or divide both sides by 5 and x equals 6. I can check my answer here by plugging in 6 for x. 6 minus 4 is 2. Log base 2 of 10 minus log base 2 of 2 is going to give me log base 2 of 5, because remember we're using the quotient property. And if I plug in 6 for x and I get a 2 as my input, 10 divided by 2 is 5, so we would get log base 2 of 5, which is the exact same thing we have on the left side, so that means our solution checks out. In part B of example 3, again, we're not solving exponential equations, we're solving logarithmic equations, and we want to solve log base 5 of x squared plus x equal to log base 5 of 20. Now, in order to use the one-to-one property, I mentioned in the previous example that in order to use the one-to-one property, you have to simplify the equations down to a single log on both sides of the equation. In this case, on the left side, I only have 1 log, and on the right side, I only have 1 log. So basically, what I'm looking at then is, are my logs the same base? I have base 5 here and base 5 here, so then we are down to a single log with the same base. So basically, those logarithms cancel out, and to solve for x, we would say x squared plus x has to equal 20. At this point, I can see that I have a quadratic trinomial. I'm going to get all 3 terms on the same side by subtracting 20 from both sides. And then I'm going to solve for x by, in this case, since my lead coefficient is 1, I can go ahead and factor this quadratic and say that x times x is going to give me my first term, or x squared. And then I want to know the numbers that multiply to be negative 20, but add to be positive 1. Well, since my product is negative, I know I'm going to have 1 positive and 1 negative number. And I know that 5 is going to be positive and 4 is going to be negative, because 5 times negative 4 is negative 20. But when I add 5 and negative 4, I do get a positive 1, which is my middle coefficient. Now, if x plus 5 times x minus 4 is equal to 0, we can use what's called the zero product property. 2 things multiplied together to give me 0 means that, or 2 factors multiplied together that equals 0 means that one or both of the factors have to equal 0. So if x plus 5 was equal to 0, if x plus 5 equals 0, then x is negative 5. And if x minus 4 is equal to 0, that means x has a solution, or a value of 4. So our 2 solutions are negative 5 and positive 4. If I double check my work here and go back into the original problem, I would substitute in negative 5 for x and make sure that I get 20 as my input, right? This whole expression here has to equal 20 because we're taking the logarithm base 5 of 20 on the right side. So negative 5 squared minus 5 is 25 minus 5, which indeed is 20. And if I plug in 4 for x, 4 squared plus 4 is 16 plus 4, which is also equal to 20. So -5 and 4 both are solutions because they give me an input value here of 20 on the left side, because my input value over on the right side is also 20. In example 3, guided practice, you are going to solve this logarithmic equation. Log base 3 of 15. 15 is my input on the left side, is equal to log base 3 of x plus log base 3 of x minus 2. And what you're going to do is solve the logarithmic equation for x. You have 4 choices. A is 5, B is -3, C, they're saying x could be -3 or 5, and 5 I should say, and D is no solution. So go ahead and work out this problem and find your solution and submit your answer, either A, B, C, or D, when you are finished.